Well, question. Okay, so there was a question in the break to make more precise the argument over the disk. Actually, in second thought, I'll do that at the end of the lecture. Still, I think there'll still be time, and I'll carry out the calculation at the end of the lecture, so that I can finish winding numbers now. Right. Okay. So, okay, I think everything is working. If anything is not, please let me know. All right, so we define this object, the winding number, right? And now we know it's an integer multiple of 2 pi I, right? Or the integral is an integer multiple of 2 pi I. So in particular, once I divide by 2 pi I, it's an integer. Okay, so what else would we like to say about this number in order for it to have some meaning? Right, so close curve, okay. You leave this here. Great. Okay, so another important thing, so proposition, right? If, let's say that I have a disk in the complex plane, right, an open disk, okay. Then if there is a curve inside a disk and A is not in the disk, right, if I have some disk, there's a curve in it, and A is outside, then the winding number should be 0, right? Because the curve doesn't go around A any time, right? It's closed inside the disk and A is outside, right? Then if I have a disk, the curve is in the disk and A is outside, then right, the winding number is equal to 0. Okay, the proof of this is almost trivial. Oh, sorry. Okay, the proof of this is almost trivial. Why? Because 1 over z minus a is analytic in the disk. And the curve is closed, so it must be 0. Right? So the integral, right, and the proof is done. Okay? That's right. 1 over z minus a is not analytic at A, but if A is outside of the disk, then there's no problem. Okay, so this number is starting to make sense. But really what we ought to show, right? What we really ought to show is that, let's say I take here, right? Right, and this is a more interesting like proposition or theorem. Okay, maybe before writing the theorem, let me write what I mean, right? Let's say that let me draw a picture first. Let's say that I have gamma like this. Okay, this is a picture of gamma. Right? Now gamma just drew over the complex plane a bunch of different regions. right? And now I can take one of these regions, say this one, right? This is a region, right? The region, right, determined, let's say, by gamma, right? It's a connected component of the complex numbers after I take gamma, right? Whatever many times gamma loops around a point, right? Another region is this one, right? This is another region, right? There's, of course, a very special region, which is the one that's outside, the one that contains the point at infinity, right? The one that's unbounded. There's only one that's unbounded, of course, if the curve is closed, right? Because the curve needs to be bounded, needs to be inside a big disk, and there's only one region that contains the outside of that big disk. Okay, but it better be that the winding number is constant in the region determined, So in particular, this is something important, right? Otherwise, this number doesn't really make much sense, right? If I have 2 points in the same region, the number of times gamma winds around that point needs to be the same, right? If I have a point A and B in the same region determined by gamma, the winding numbers must be the same, right? So gamma, closed curve in the complex plane. If A and B in the complex plane are in the same region determined by gamma, then their winding numbers need to be the same. So n gamma A needs to be the same as n gamma B. Okay, the proof of this is less obvious, right? I mean, intuitively it makes a lot of sense, but how do we argue this? Right, so the proof is a little less obvious. Okay, first of all, we know because this region is an open connected set, right? A and B can be connected by polygon lines. Or linked, I should say, maybe, by polygon lines. Right? So without loss of generality, right? Without loss of generality, I can just assume that by polygon lines not intersecting gamma, of course, right? Still inside the region, not intersecting gamma. Right? So without loss of generality, I can just assume that they're in just one segment. Because if I can show that this number is the same along segments, then it needs to be the same also in all the connected region. Right? If, say, I drew here points where they are connected by lines, but let's say that I have a point C here, right? I can just go from A to C by showing that it's the same if I do it on bad line. On lines, it will be the same as this point, and then it will be the same as C. Right? So without loss of generality, we can assume that the line segment between A and B doesn't intersect gamma. Okay? And now there's a trick, right? So now the trick is to observe the following. Is to observe that if I take Z minus A over Z minus B, right? Outside of the segment, so outside of the line segment, of the line segment, A, B, right? Then if we think about this number, let's think about the argument of this number, right? The angle of this number. For any Z, right, there's Z minus A, right? So there's this vector. We can think of it as this complex number and this one. But outside of the line, outside of this line segment, the relative angle between these two vectors is never 180 degrees, right? Because the argument of this quotient is the argument up here, the argument on the numerator divided by the argument of the numerator. This number is never, outside of the circle, the argument of this number is never pi, right? And so in particular, this number, the line segment, is never, say, negative real. Okay. And if it's never negative real, then I can define the logarithm just on the so-called primitive branch, the principal branch, right? So I can define, right, the so-called principal branch. Right, I think you saw a lot about branches on exercise class. The principal branch of the logarithm of this number, right? Just where the argument, where I take the argument, right? I take the imaginary part to be between minus pi, minus pi and pi, right? I never loop around because I always avoid. This is the complex plane. I never go, right? This number never goes into the, never, right? It's everywhere, but it never crosses the pink line. And so I can just define the argument in a, right, in a nice way between minus pi and pi, and I never have the issue of looping around. Okay, right? Imaginary part or, right, imaginary part or argument. Okay. And in fact, this is a derivative there, right? It's nice and analytic, right? And define a principal branch is analytic, right? Is analytic outside this line segment, right? Line segment. So in particular, it's analytic on gamma. Okay, so I think I need to erase first one. Okay, and so particularly it's analytic in gamma, and there and outside, right? Outside the line segment, right, between A and B, right? There has a derivative, and the derivative is just, right? I'll spare you of the actual derivative calculation. This will work out to be 1 over z minus a minus 1 over z minus b, right? Just use chain rule and the derivative of the quotient. Okay. And so it means in particular, right? It means in particular that this function has a primitive, right? This function has a primitive outside of the line segment. Okay, but if it has a primitive outside of the line segment, then because gamma doesn't intersect the line segment, it must be that the integral of this is 0. And we're done, right? Right, because gamma doesn't intersect, right? Gamma intersected with, okay, right? This line segment is nothing, right? And so in particular, this implies, right? This is just the winding number of A and the winding number of B minus the winding number of B. This is 0, so we're done, right? Right, this is a slick trick. Okay, and so we're done. Okay. Now, this means also in particular, almost immediately, right, that in the unbounded region, right, in the unbounded region, if I have a point here, let's say a point, right, let's say a point W here, then the winding number of this one needs to be 0. Right? Why? Because I can just use the two theorems that I just proved, right? Because I can just take, I don't know if I can do this on this picture. Let's see. Right? I can just take a big disk that encapsulates the whole curve. Right? If I take a big disk that encapsulates the whole curve, and I grab a point here, right? Let's say I have a point here, H. Then, because the curve is all inside the disk and H is outside the disk, right? Then the winding number of the curve with respect to H is 0 by the first proposition that we showed. No, but these are in the same region. So by this other, and I mean, if I had put it here, I could just go around, of course, by 2 lines, right? And so this one must be the same, and so the winding number on the outside, on the unbounded region, is always 0. Okay, we just proved that basically. Okay, so I think that's all about winding numbers. Maybe let me show something else actually before we move on. Okay, so the winding number, is an integer. It's well defined in the sense that if I move within the region, it stays constant. The winding number on the unbounded region is always 0. That is all things that would like to hold if it really is to mean the number of loops that a curve does around a point. Okay, now I'll just work out an example. This example is in the book, so you can see it there more carefully. I'll do it a bit less rigorously just to show you the kind of things that one can do. And then, since it's the same example, you can just see it more rigorously in the book if you like. Right, so let's say that we would like to say that if I have a point, right, it can be 0, say, right, or A, right, and if I have a curve like this, right, we would like to say that, the curve that it's 1, right, that the winding number of this curve around A is 1. Right, this is sort of our intuition. So let's try to make a theorem that makes this intuition a little more precise. So one way that you can do this is by taking a point on the curve. Let's call this Z plus. Let's take another point, Z minus. Okay, and let's say that this point is actually just 0, just to make things simpler. Okay, so this point is 0. And now I have a point. I'm taking a point such that the real part of Z plus is positive, and the point such that the real part of Z minus is negative. And now I want to capture this fact that gamma loops around. right? And so one way that I can do that is by saying that splitting gamma into two curves, I'm going to split gamma into the gamma that goes from minus to plus. Let me call this gamma upwards. And one that goes from the plus to the minus. Let me call this gamma downwards. Okay. And of course, if the curve was to go around the other direction, the winding number would, of course, be negative, right? The winding number of the circle going the other direction of minus the curve is just minus the winding number, right? But I want to argue that if the curve goes around this way, then it must be that, right? Then it must be that the winding number is 1. Okay, so how do I argue this? Well, one way that we could potentially do that is by saying, let's assume that the part of the curve going up doesn't intersect the negative reals. Right? And the part of the curve going down doesn't intersect the positive reals. Okay, if I have a curve like this, where I have a point up here, a point down here, and this curve doesn't intersect the negative reals, right? So it goes around this way, then comes around the other way, right? Because this one doesn't intersect the positive reals, right? It could be that it does all sorts of weird things here, right? It could be doing this, right? That doesn't matter, right? But this is one way of capturing that really the winding number should be 1. These conditions, right, should imply that the winding number is 0 is 1. Yeah, okay, sorry. Right, so how can we argue something like this? Right, it's actually quite easy. So let me take away one of these loops just to make it easier for me to draw the picture. But of course, it could loop it or whatever many times it desires. Let me just to make the picture a bit easier to draw. Okay, so the idea, right, if we want to argue that a curve like this has winding number 1, what we can do is we can compare it to a circle, because we know the circle is winding number 1. Right, and so we can take a circle, right, because the curve doesn't intersect 0, right? That's of course important, right? The curve itself zero cannot be in the curve, right? So I take a circle, C, right? And now I just have to think of these paths. So take this path, take the path that goes here, right, around. So let's take this line and take that line. Let me see if I can do this with enough colors. Okay, so let's take this path, and let's now take the path that goes this way. Okay, so let's take the path that does this. This goes around here, then comes back this way, and comes back on C. Right, so take this pink path. And now let's take a green path that goes this way on gamma downwards, goes up this direction, goes around the circle like this, and then up here, right, and then, of course, this way. Okay, so now, right, if we think about what this means, the winding number, right, of gamma with respect to 0, right, is some integral, right? The integral should be the integral of the path in green. Let's give it a name, alpha downwards, and this one in pink will be alpha upwards. Right, so this should be equal to the integral around alpha upwards, 0, plus the integral alpha downwards, 0. Okay, but now what I did was I now integrated also around the circle, right? This sum integrates, right? These ones cancel out. It integrates around the blue curve, but it integrates the other way around the circle once too many times, right? So I need to add back the circle, right? Because when I take these two paths, I integrate around the circle the other way, so I need to add it here. Okay, but we know, right? This one, 0 is in the region, in the unbounded region of alpha upwards. So this is 0, right? Same thing here, right? Because the point 0, right, from the viewpoint of alpha upwards is outside the area delimited by this curve. The same thing for downwards. And this we know is 1, right? And so we show that this is 1, okay? Just to exemplify that, this really sort of means the number of times you go around a curve, and you can make it precise, right? It's hard to make that into a precise definition, but you can try to prove things that make sense, right? If I, right, in particular, if I had a point above the real axis, one below, and when I go up, I go on the positive reals. When I go down, I go through the negative reals. This should have definitely looped around once, and you can indeed make that precise. Okay. Hope the pictures were clear. Let's now finally get to the integrand formula, and then I leave a bit of time to make a bit more clear.
One question.
Yeah, go ahead. Oh, I wasn't looking at the chat. Yeah.
Which asks why we do add the winding number.
Yeah. Okay. So maybe the right way. Really, maybe what I should have written is that n maybe this is better. Minus, sorry. Okay, let me be a bit more suggestive. This is really the equation maybe I should have written, right? Why is this equation true? Because going around alpha plus, right? I go around like this, and then go around. And then going around alpha downwards, right? I go around like this. What did I do? These two cancel out. So in total, I went around the blue curve, and I went around the circle pointing the other way, right? I can take this circle, which is minus the circle, right? Because I had to go around the circle pointing the other way. And so the integral going around alpha upwards plus alpha downwards is the same thing as going around the blue curve plus going around the reverse of the circle, right? But the reverse of the circle is equal to minus the winding number of the circle, right? And then that circle went to the other side. Yeah, I should have done this intermediate step. Did that answer the question? Okay, if not, please just, write on the chat if anything is still not clear. Okay. All right, so let me see if I want to say anything else about... No, I think, great. Okay, I think we're ready for the integral formula, which will be really the workhorse of a lot of what we're going to do. So, okay. Okay, so Kosher. Okay, and this will be a very important I mean, by now we've done all the work to prove it, so proving it won't be difficult at all, but it will be extremely useful for what's yet to come. Okay, so let's just stay in the disk. So theorem, let F on the disk to C be analytic. An open disk. Okay, of course, an open disk inside a complex plane. And gamma closed curve. Okay, so we want a closed curve contained in the disk for a not in the curve. Right? We have, right, for a not in the curve, we have that the integral, okay, and now is the this will maybe feel like it comes out of nowhere, but we'll prove this, and you'll see we've built up everything to prove it. Right? And this is the integral formula. Okay, why is this so useful? Right? The reason why this is so useful is that, let's see.
I think you forgot the 2 pi I.
I did forget the 2 pi I. Thank you. Yes, good point. Do I want to put it in there or yeah, here? Thank you. The gamma A F of A. Okay, so we'll see that proving this actually we've done everything already. So this will be very easy. Let me just convince you first that this is going to be extremely useful. Right? So here we get the value of a function at a point A. And we're saying that the function of a value of a point A is given by the function by the function value at Z over some curve that we can even pick. Right? So this means in particular that sorry, chalk everywhere. So if right, we can determine the value of function f by the value of the function in a curve that we can even pick. In particular, if we pick a curve that goes around A exactly once, then we have that f of A, right? And the winding number will be 1, so f of A will be equal to this integral. So this will allow us to do lots and lots of things. For example, if f somehow, right, if we're in a singularity, we don't know what f of A should be, right? We get the function that's defined everywhere but in a point. If we can define it, right, if we have a point A, we don't know what the function should be here, but we want to build a function, an analytic function here. One thing we can try to do, right, is draw, say, a circle around and make the value of f of A be equal to this integral around, right? So it will allow us to extend functions to some extent. It will also allow us to take derivatives of f, even if we don't know what derivatives would look like, right? Because if I now think of A as a variable and I fix a curve such that the winding number is 1, I can take derivative with respect to A here, and I should be able to take, I mean, we need to justify it, but I should be able to take a derivative inside the integral, right? And this doesn't change. All that changes is Z minus A will become like Z minus A square, right? And so this will allow me to start writing formulas, integral formulas, not only for the function, but for the derivatives. And this is sort of the key reason of why analytic functions are so smooth and so regular. Because after I have such a formula, right, once I want to take derivatives with respect to A, it says as regular, as nice as 1 over Z minus A, right? Because when I take derivatives inside the integral, only this part gets a derivative on it. And so this is sort of the turning point in which you start seeing why these functions are so regular, right? It's exactly because of this formula. Okay, so let's prove it. And most of the theorems about regularity of analytic functions will come from this. Okay, all right, so, okay, prove. Okay, so the proof is very simple. We just write, right? We just apply, right? Apply Cauchy's theorem on a disk to the function f of z equals right? Right? Clearly, f is analytic. Analytic in delta without a, right? Because f is analytic. Okay. Also, a is a special point in the sense that the limit of z going to a of z minus a, right? F of z, right? This is equal to 0. This was exactly the motivation to think about these kinds of special points. Why? Because if I do this, this is just the limit when z goes to a of f of z minus f of a, right? And this is just equal to 0, right? So we can apply Cauchy's theorem on a disk with the exceptional points. And so if we do that, what we get is, right? So we get that the integral over the curve of f of z needs to be equal to 0, right? By Cauchy's theorem, right? But this is the same thing exactly as is saying that the integral of this, so f of z minus a dz, right, minus f of a z minus a dz is equal to 0, right? But now we're done, right? So this integral f of z minus a dz is equal to, the f of a can come outside, right? This is equal to that. The f of a can come outside of the integral. So we get f of a, and then we get 2 pi I times the winding number of gamma a, right? Because this is exactly f of a times the winding number of gamma a. Okay? So this is one of the most important theorems in, one of the most useful we're going to do. Okay, and so let's maybe take a second. So now we're able to, given the function of f at some points, we can say what it is at a, right? The proof was almost completely trivial given what we already had, right? In particular, that this sort of justifies why we wanted to understand those special points. And the way we should think of this really is think of it for curves where, right, you should really keep in mind curves, right? For curves for which n gamma a is equal to 1, then this is really sort of a representation. You can view this as a representation formula. Why? Because there, what we really have is that f of a, right, is equal to 1 over 2 pi I integral of f of z minus a dz. right? And so actually what's very useful to do is to, because we're soon going to want to differentiate with respect to A to talk about regularity of, to use the formula to talk about regularity of these functions. Actually, it's very useful to, instead of A, just call it Z. So I'm going to just change the notation. And the way that we usually write these formulas is this way, right? Right? If we want a sort of a representation formula that we can use over and over again, okay, is if, right, take a curve that just goes around one, like a circle, for example, right? And then we write, or Z, I should say, right? We should write one over, and now let's do C minus Z, oh, sorry, f of C, right? The new dummy variable which we integrate over. Okay. And in particular, if we have, right, we can take the curve to be a circle. So right, so let's Z be a circle inside the disk, right, where f is analytic, and for all, right, we know for all points inside the circle, for all points Z inside the circle, right? By inside the circle, I mean inside the, right, the circle is the boundary of some other disk. Inside that, inside C, we have that f of Z is equal to the integral of 1 over 2 pi, integral over the circle of f of C, right? C minus Z, sorry, C minus Z, dxc. Okay. And so this now gives us a representation formula, right, of f in a circle around. And so as long as a function is analytic, right, it'll be analytic in a little open set around the point, I can always come up with a circle around that point. And so I can always talk about this, right? I can always talk about this representation function. And then I'm going to be able to say things about derivatives of f by just differentiating inside of the integral on this variable that's no longer on the function. Okay, so now I'll stop here. We'll talk about higher derivatives on Friday. But I'll talk a little bit about, I'll see if there's questions. I'll talk a little bit about the proof with the exact differential again, just in case it's not fully clear. Okay, let me just have a bit of water because I think I got chalk. Okay, any questions, or should we do the... Yeah, I'll just talk a little bit about the exact differential again, in case something was not clear. What did I write? All right, so the problem is that there's the need for so many dummy variables, or you just do abusive notation, call everything the same, and then it's really confusing. Let me just use the dummy variables. Try to keep track of all the variables. I think this should be enough. Okay, so let's take, right, this will be a point z0. Let's call this x0, y0. Or maybe instead of that, I'll just call it x0 plus iy0. I mean, I'm doing the identification with then there's some point, say z1, which is x1 plus I y1, right? And let's say I take a curve like this. Let's call this gamma 2. Gamma 2 has two parts, right? As gamma 2 upwards and gamma 2 horizontal. Maybe I shouldn't write there because it might seem like it's conjugate. Right? And so the integral over gamma 2 of f of z dz is equal to the integral, right, over gamma 2 upwards, the same thing, f of z dz, plus integral gamma 2 horizontal, f of z dz, right? But now I want to argue, right, since I define f of z1, big F of z1 this way, right? I mean, or in other words, f of x1 plus y1, right? And I want to argue that the derivative with respect to x, right? I want to argue that the derivative of f with respect to the real part that is equal to f of z, right? So you should imagine this path, right, as going a bit, right, like you want to take the derivative of as this path varies to go from z1 or to go from z1 plus a little bit, right? The same argument as with as what we did with the exact differentials, exactly the same thing, right? And so, right, what happens here doesn't matter. The only thing that matters is what happens here, right? This part is fixed. As I vary on x, this doesn't change, only this changes, right? So if I take now the derivative, say, with respect to x, right? Or maybe I should write this in another way. Let's say, I would like to do this without introducing any more dummy variables. Okay, let's say that I do, right? I have this gamma 2 upwards, f of z dz. And now I'm going to parameterize this curve, right? But this gamma 2, right, is just a curve that goes from, I don't know, in this language, it's, so it's x0 plus I y1 to x1 plus I y2, right? So I can just parameterize by t being from x1 to x2 to x0 from, right? I can just parameterize that t this way, and the curve can just be z of t equals to t plus I y1. Right? And now if I take this integral, I just have the integral from, right, in the parameterization from x0 to x1, right? And this part is fixed, right? Integral from x0 to x1 to f of the curve, so f of t plus I y1 times the derivative of the curve, but the derivative of the curve is just 1, right? So, right, this derivative is just 1, right? Because when I differentiate with respect to t, I get just 1, right? dt. Okay, and so f of x1 plus y1, right? I mean, I'm doing, okay. But now if I take the derivative of this with respect to x, to the variable x, this part, nothing happens to it, right? This doesn't depend on x. This integration is just in the right, is always in x0, doesn't depend on what happens in x1. So when I take the derivative, right, of f with respect to x, say at the point x1 plus I y1, right, what is this equal to? This part has derivative 0. Is just equal to f at point x1, right? It's just equal to f at, sorry that this is like quite, Right? It's just f at, maybe I'll just erase here because it's a bit too dirty. And right, so where was I? Respect to x of is equal to, right? This is 0. This is just by fundamental theorem of calculus, f when t gets replaced by x1. Right? And so this is equal, this means, right, I wrote this in the other language, which was that integral of f with respect to x was equal to f. Right, that's exactly what's written there. Now, if I do it the other way, right, I won't redo all the calculations, but if I do it now this way, in which I go first this way, and then this way, right, I have a gamma 1 horizontal, a gamma 1 upwards, right? Here I'll have the gamma 1 horizontal, here I'll have the gamma 1 upwards. Now, the way to parameterize gamma 1 upwards, right, so gamma 1 upwards, how would I parameterize it? Right, I'll parameterize it by z of t being now x1 is fixed, right, just like there, plus it, and t being between y0 and y1, right? And now means that the derivative, right, now the derivative of zt is I, right? Here I don't even have to introduce the dz equals dx plus I dy, right? This derivative is I, and so when I do this, instead of a 1, I get an I, and so I get that the derivative with respect to y of this is equal to, right, the same thing will happen, f, but there's an I from this derivative, so it will become derivative of f. I'll do here because respect to y equals if, right? And then these are the Cauchy-Riemann equations, right? Another way to think about it, I mean, let me see. Okay, give me a second to see how I want to say this. Maybe one good way of thinking about this is that, right, we could have tried to do this. I think a fair question is, why did we go into the reals to do this? Why didn't we just build f, build f in this integral and just stayed in the complex numbers and never went to the reals in order to do this? Okay, I think that's a fair question. So let me see what's the best way of answering this question. I guess I'm now asking questions and answering them. But so, right, so the thing is that the definition of derivative over the complex plane, right, the definition of analytic is that the derivative, the limit that defines the derivative, regardless of the direction it comes from, is the same, right, that they're all compatible. So in order for you to say that something is analytic, you would have to investigate this limit coming from all possible directions. But in this construction, right, we only get to say something about these limits via the fundamental theorem of calculus from the direction in which we take the curve, right? And we want to use the fact that we know this theorem about the rectangle, so we have access to two directions. But something that we did back in the beginning of the course, the Cauchy-Riemann equations, allows us basically to say that if the derivatives are over two directions, the limits in two directions, the reals and the complex, are compatible in the sense that the derivative over the imaginary part is I times the derivative over the real part, then this is enough to make sure that the limits over all directions are okay, right? If you remember a function of two variables, once you know, as long as things are nice and continuous, once you know the derivative from two orthogonal directions, right? They're a basis of the linear space of the possible directions, you know the derivative from everywhere. And so this result that we showed about Cauchy-Riemann equations allows us to argue that if we have limits, if derivatives are compatible just in two orthogonal directions, coming from the reals, coming from the imaginary, then the function needs to be analytic, which implies that they're all compatible from all directions. And that's why going to the reals helps a lot in this part of when we're deriving things in complex analysis, because we can go to the reals. We just have to guarantee compatibility between x direction and y direction. Because of this thing we proved about Cauchy-Riemann equations, we get compatibility of every direction. and then this allows you to make sure that it's analytic over the complex numbers. To do this just within the complex numbers, I think would be a bit more challenging. I would have to think about how to do this properly, but I mean, without defining such a thing as a real part and imaginary part, it's not quite clear how, right, we could try to start making theorems. Instead of the rectangle, we could have made theorems over triangles and use the exact same argument of like bisecting the triangles. And once we have triangles, we could come from any direction. Probably something like this would work, but this is definitely a lot simpler. Okay, this was a long answer for a short question. Hope it clarified. All right.